Assalamualaikum, welcome back to my lecture. So this is casting part 3. In this topic we are going to discuss about the heating and pouring in casting. In order to get the molten metal, heating of the metal is needed. So heating furnaces are used to heat the metal to molten temperature sufficient for the casting. So the heat required in the heating of the metal is the sum of heat to raise temperature to melting point, heat of fusion to convert from solid to liquid, and the third one is heat to raise molten metal to desired temperature for pouring. So this heat is summarized into this equation where H is the total heat required to raise the temperature of the metal. So then next is the density, and V is the volume of the metal being heated. Now here come the three heat. So this first part is the heat to raise the temperature to melt the work material. So if you can see, this CS is the weight specific heat of the metal. So this one you get it from the table. Tm is the melting temperature of the work material, and T note is the starting material, usually the ambience temperature. So let's say if it is room temperature, then it will be around 25 to 27 degrees Celsius. So HF is the heat of fusion. Okay, so this one also usually you get it from the table. And then Cl is the weight specific heat of the liquid metal. Okay, so this part is for the heat required for the to get the pouring rate. Okay, so Tp is the pouring temperature and Tm is the melting temperature. So that's how you get the total heat required to raise the temperature of the metal to the pouring temperature. Now let's see some example. Okay, so 1 cubic meter of a certain eutectic alloy is heated in a crucible from room temperature to 100 degrees Celsius above its melting point for casting. The alloy's density equal to 7.5, melting point 800 degrees Celsius, specific heat 0.33, solid state in the solid state and 0.29 in the liquid state. So the heat effusion is 160. How much heat energy must be added to accomplish heating assuming no losses? So what you're supposed to do to solve the problem is write the formula. First, you write all the formula so that we can determine what are the things that's already there and what are the missing part. Okay, so the first one is density. So the density is already here. And then V, volume, is already given 1 cubic meter. And then CS is already given here 0.33. And then Tm, melting temperature, is 800 degrees Celsius. And then T note is not given, right? So T note is not given. HF, heat fusion, is already given 160. And then Cl is also already given 0.29 in liquid, right? So Tp, no Tp, right? Tm is 800 degrees Celsius. Okay, so this part is not given. Okay, now T note is not given, but we can assume that T note is the ambience temperature, so you can assume like it is to 25 degrees Celsius. Let's say, for example, inside here, it can go to 25 degrees Celsius. If it is not given, you can use 25 degrees Celsius or 27, up to 27 degrees Celsius. So usually we use 25 degrees Celsius. Okay, so now T note we already assume. Now next is Tp minus Tm. Okay, so where it is stated the Tp value. So if you go back to the first one, 1 cubic meter of a certain eutectic alloy is heated in a crucible from room temperature to 100 degrees Celsius above its melting point for casting. If it is 100 degrees Celsius above melting point, it is 800 plus 100. So this is the pouring temperature. Okay, So we can assume that this one is 900 and this one is 800. So it is equal to 100 degree Celsius. Okay, so once we already have the value, so you just put it inside here and then you will be able to do the calculation. So in here it's already solved up to this one. Okay. For pouring the molten metal, for this step to be successful, metal must flow into all regions of the mold, most importantly the main cavity, before it can solidify. So the success of pouring is determined by these three factors. One is pouring rate, another one is pouring temperature, and the last one is the turbulence. So the pouring temperature is the temperature of the molten metal as it is introduced into the mold. So what is important here is the difference between the temperature at pouring and also the temperature at which freezing begins. So this one have to refer back to the melting point for a pure metal and the liquidus temperature for the alloy. As for the pouring rate, it is the volumetric rate at which the molten metal is poured into the mold. So for example, this is the cavity, and then how fast you pour the molten metal into this cavity. Okay, so this one is very important. The pouring rate cannot be too fast and cannot be too slow. If it is too fast, it will create turbulence to the casting, and it can be a very serious problem. And if it is too slow, the metal will chill and freeze before the metal fill in the cavity inside here. Okay, so that's why it cannot be too fast, or it cannot be too slow. So what is turbulence? Turbulence is a fluid flow characterized by erratic variation in magnitude and direction of the velocity throughout the fluid. So instead of, for example, if we pour the metal, so instead of a steady and flow, so what happen is there will be like a more erratic in terms of the molten metal coming inside the cavity. So this flow is agitated and irregular rather than smooth and streamlined as it laminar flow. So what happened here is when this happen, the heat will be trapped inside here and it will start to accumulate inside the casting and inside the sand. So this is what we don't want inside the um, casting inside the. So turbulence will create some disadvantages. For example, it accelerates the formation of metal oxide that can become entrapped during solidification. Thus, it will degrade the quality of the casting because you know it can metal oxide is the corrosion, right? Okay, so mold erosion, so there will be wear away the mold surfaces due to the impact of flowing molten metal. And the third one, the geometry of the cast part is affected due to the mold erosion. So in here I give you the problem and its solution also. First, don't see the solution first. Try to solve the problem using the previous one and the tips that given inside the slide. Okay, so after you already solve the problem, then you can see the solution in the final slide. So here to find the value for the material, you can refer to this table. For example, you can find the density, the coefficient of thermal expansion and melting point inside here. So in here you can find the value for specific heat and also thermal conductivity. And so this is the solution for the question. So that is the end of casting part 3. So we are going to continue with casting part 4 later.